thank you very much. And thank you very much for inviting me to this very exciting workshop. I've never been at a meeting like this, so it's really interesting. Okay, so I'm going to talk about something sort of very different, and it's really an example of applying basically some of the concepts that we have been talking about. So really looking at data and see what can we learn about cosmological magnetic fields. So I will explain a bit about how I'm going about these. So first of all, I'm just talking in general about observational evidence of magnetic fields in the universe. And then later we'll focus on cosmological magnetic fields and how to actually constrain these type of fields with data. And I will actually look at a very particular example, a part of the theory basically to be tested. Okay, so basically I think that everybody knows that there are magnetic fields in our world. So from our magnetic field of the Earth, solar magnetic fields, then further on in the galaxies, in most galaxies, and beyond even that. One of the big questions is where there's still really a debate about is the existence of cosmological magnetic fields, real, truly cosmological magnetic fields that actually pervade the whole universe. And there's basically really the direct observational evidence is basically, there's no direct observational evidence. It's really all implicit, and this I will discuss basically as I go along in the talk. Okay, so what are observational tracers of magnetic fields basically beyond solar system scale? And there are different effects that one basically can use. So one of them is synchrotron radiation, then there's a Faraday rotation, there's a polarization of starlight, and then I will also comment on these void magnetic fields, which are basically used to point towards the evidence of truly cosmological magnetic fields. So I will try to be very simple, and I will try to I don't expect you to really understand all the physics involved in that. I mean, the only thing that I want to transmit with that is basically the tools that astrophysicists or cosmologists are using in order to deduce the presence of galactic magnetic fields or cluster magnetic fields and beyond those scales. And so I will start basically with something which is synchrotron radiation. Okay, there basically in galaxies we have, there are galaxies, they are formed of stars. Basically we have different stars like our own sun in the solar system, and in between there's it's not empty. I mean, there's there we have dust, for example, is also one of the important components, and there are also free charge particles like electrons. And if there's a magnetic field, what these charged particles tend to do is basically spiraling around these magnetic field lines, and while they're doing that, they're emitting radiation, and this radiation is synchrotron radiation, and in those type of settings in a galaxy, it's basically in the part of radio emission, so it's being detected with radio telescopes. And from that one can actually make an estimate of the magnetic field strength that one needs if one observes a certain amount in intensity of this type of radio emission. And with that we can, knowing something about basically or making assumptions about the medium where it takes place, one can actually estimate the magnetic field strength. So this is basically one way of deducing the presence of magnetic fields. And as we already see here, it's not direct. What we need actually is to observe the synchrotron radio emission. So it's not something like we can go on Earth and we take a compass or something like this, and then we can detect directly the direction of the magnetic field lines, etc. And here it's really an indirect way. We need the radio emission in order to deduce something like the presence of a magnetic field. And these are typical observations. This is a spiral galaxy M51, and this is the synchrotron radiation that's observed. And basically using the model, basically one can deduce the field strength in the direction, and they usually follow the spiral arms. This is another example, which is in a different frequency range, but it's also radio and synchrotron emission from a different type of galaxy. In this case, okay, we can also again deduce the magnetic field strength that we have there. As I already said, I mean, magnetic fields, they are also observed not only in galaxies, they are also observed in clusters of galaxies. So these are just groups, accumulations of galaxies, and they also form bound systems. And so these are galaxy clusters, and they also are associated with magnetic fields. And this is an example of one of these type of clusters, and the synchrotron radiation of that. And okay, as I said, I mean, this is one way of measuring magnetic fields in the universe. Another one is something which is called Faraday rotation. In that case, what is important again is radiation. But in this case, it's another aspect of radiation, which is the polarization. So, if we have a radio galaxy and it's emitting linearized, basically radiation with a linear polarization. Okay, so electromagnetic radiation is basically described by two fields, on the electric and the magnetic field. They are perpendicular, and if it's linear polarized, then the electric field, for example, I mean, just to explain them, the electric field vector is basically oscillating in just one direction, and then we have a linear polarization, what we say. And if this type of radiation is passing through a region, like for example a cluster of galaxies, where there are free electrons and also a magnetic field, then what is happening is that this plane of polarization of the radiation which is emitted from the radio galaxy is actually turned. And if one observes at different wavelengths, then one can actually determine this type of rotation measure, basically how much the plane of polarization is changed. And with that, again, we can estimate the magnetic field strength. If you also know, again, something about the medium which we have here in this class of galaxies. Again, it's an indirect measurement, I mean, of the magnetic field. I mean, we have basically let's say, I mean, maybe I can basically interpret it as what we were saying before. I mean, we have the observation, we have the evidence that the plane of polarization was rotated, and the explanation in this case is the existence of a magnetic field in this area. So this is another way, and typically one can do actually a whole, I mean, this is of our galactic magnetic field. I mean, basically one needs background sources, and then one can basically do it for the whole sky. And this is an all-sky map of the galactic magnetic field of basically of our own galaxy. And typically, has done observations like this, and these red and blue points, these correspond to if this change in the angle of the polarization is positive or negative, and that's basically on the direction of the magnetic field. And again, we have also observations of these on cluster scales for cluster magnetic fields, and even beyond cluster scales. So there are also structures which are superclusters, which are really on much larger scale. And so another way this I also wanted to show, because it's a picture later on from Planck, which is also very impressive, from our own galactic magnetic field. So there's another way on which basically we can deduce the presence of magnetic fields, and now this is also in a different frequency range, and this actually is due to dust emission, I mean dust thermal emission, and this is basically in the infrared. Okay, so basically, as I already said, I mean in our galaxy, in the interstellar medium, there's dust, and dust grains. They are, if they are asymmetrical, which are basically most of them are, then they, in this case, I mean, there are different mechanisms, but one of the mechanisms is that they actually absorb part of the stellar light, and they absorb it along the longer direction, the direction of the longer axis, and so basically part of the light is absorbed, and then basically what stays is basically polarized, the polarized part. And dust grains, they also emit radiation, and this is in the infrared, and they also do it along the longer axis, and again it's then polarized, and this actually has been observed by Planck satellite. This is of the 353 gigahertz channel, and this actually is a picture of the polarized dust emission of dust in our own galaxy, and it's tracing actually the magnetic field, our galactic magnetic field. So again, here we see, I mean, we already saw several of these pictures. So again, here we have the galactic plane, and there we have the magnetic field basically follows, is in parallel to the galactic plane, and then going away from that, the field becomes much more less ordered, and this is basically what's reflected. Also these field lines which become much more. But this is really quite impressive, because it really looks more like artwork, but it's an observation. I mean, this is really, whenever I look at it, it's really fascinating. Okay, so far I always talked about magnetic fields which are actually associated with structures, so with galaxies and clusters, etc. And then one of the big questions, or basically one of the questions that motivates me, is to find out if there exist really truly cosmological magnetic fields, I mean, which are not associated with collapsed structures. And why am I interested in that is that one part of the theories as to the origin of galactic magnetic fields is that there is a seed field. There's an initial seed field when the galaxies are forming, and this seed field is amplified during the evolution of the galaxy.
So seed field?
So it's an initial, exactly. So it's an initial field that one needs, and so that it can be amplified during the evolution, and then the galaxies basically end up with the galactic magnetic fields that one observes, and basically it's so common to observe. I mean, it's basically all of the galaxies. I mean, the spiral galaxies certainly are associated with galactic fields. So one of the big questions is, what is the origin? And one of the big group of theories basically puts the origin of these type of fields in the very young universe. But if that is the case, then there should be also some evidence for that in other observables. So we could basically test the theories to the presence of such a cosmological primordial magnetic fields. And that's basically what I'm studying. I mean, different types of observables that one could use in order to deduce if there's a primordial magnetic field. And okay, so then before going really to the cosmological part and to the very early universe, etc., I just wanted to show something which has been debated over the last, it started basically with the first papers in 2010, and since then there basically is some advances on that, but it still is an open debate. And this is basically the question, are there magnetic fields which are not associated with structure? So they are not directly within a galaxy, but they're actually in a void. I mean, so where there are no galaxies. And this is a typical galaxy redshift survey. And these are here on this part. These are different surveys and actually observations. So here in blue, and what one can see is that basically they have this quite inhomogeneous structure. And all the points, I mean, each of the points that we see here in blue corresponds to a galaxy, and where there's no point, basically, there's a void. I mean, so there are no galaxies. And just to compare, I mean, these are simulations, numerical simulations from the Virgo Consortium, and they did this huge millennium simulation, and basically reproduce also this inhomogeneous structure, what is actually observed. So, this is also impressive. Yeah, I mean, basically, we are getting, we are advancing basically also very much on the understanding of this large-scale structure. Okay, so then the question is, is there any evidence for magnetic fields in these type of voids? And actually there is, and again, it's a very different method, again, indirect, and that's also why it's still very, very much debated. Okay, and how did this come about is that, okay, in the universe there are objects, very high energetic objects, which are called blazars, and these are basically the nuclei, active galactic nuclei, and they emit radiation in very, very high energetic radiation. So it's a TeV. I mean, it's really, really high energetic radiation jets, basically, and these radiation interacts with something which is called the extragalactic background light. So with those, I mean, there's basically from all the galaxies, etc. Galaxies, there are photons in the universe, and they interact. And what is happening there is they produce electron-positron pairs. So they produce particles, high energetic particles, these electrons, and these electrons, they interact with CMB photons. So photons which are at much lower energy of the, and these are is part of the radiation of the cosmic microwave background, and they do what is called inverse scattering. But basically, I mean, the important point is that the rather low energetic photons of the CMB, they are basically bumped up to very high energy because they scatter on these high relativistic electrons. No? And in principle, then they emit basically radiation which is in the GeV range. Okay, so the point of this is, okay, we have high energetic radiation which comes from this object. We can observe this high energetic part, and there's a different experiment which actually observes this lower energy part. And the evidence for a magnetic field comes actually from the non-observation of this GeV part, of the slightly lower energetic radiation. So again, this indirect evidence that is then interpreted as due to the presence of a magnetic field. Okay, so these are basically the observations that we have. So this part is the high energetic part which comes from these blazers from the TeV part. So this really high energetic part, the original part of the radiation is observed from this high energetic object. And then in principle, if there's no magnetic field, then we would also expect to see this lower end, of the spectrum, and there are basically for most of the objects, for most of these lasers, this is actually what is observed. But there are a few basically where this is not observed. And the interpretation was then that we need a magnetic field in the intervening region which actually deviates these electrons out of our line of sight. So basically what is happening is that once these electron-positron pairs are created here, if there's no magnetic field, then basically they just follow their usual paths, and the radiation which is due to the scattering of the CMB photons, we would basically observe here. If there's a magnetic field, then again these charged particles, they feel the magnetic field and they're deviated out of the line of sight, and then we don't observe this radiation. And that's basically the interpretation of the non-observation of this part, part of the spectrum that has been basically proposed. And then again, this depends highly on the model that one actually assumes for the sources, for the propagation of these particles, etc. But several groups, they basically have come to lower bounds on the magnetic field in these regions. And interestingly here is also with these type of observations, it's actually a lower bound. It's not an upper bound. Usually with the other observations that are showed with the synchrotron emission, etc., usually one would get upper bounds. But here in this case, actually we need a magnetic field in order to explain the observations. Okay. So that's also what I want to show, and this is basically one of the one of the more or less direct observations, indications of the existence of a truly cosmological magnetic field. Okay, and now what I wanted to come to now is to actually come to the part of the more cosmological part of observations or indications of primordial magnetic fields, and I will just be schematic about it. So if you have cosmological magnetic fields, so now I'm going to talk about magnetic fields which are really pervading the universe, and we can ask basically different questions, and some of them is, for example, the origin. Where do we put the origin of these type of cosmological magnetic fields? So I will come to that just also with another cartoon in a moment. And then how do we describe it? This is also another part which is important, because as I will show, they cannot be just a homogeneous magnetic field. They have to be stochastic magnetic fields, because we have other observations already which exclude homogeneous magnetic fields, because they would just pick out a particular direction. And then the global observed isotropy of the universe that we see, for example, in the CMB, I mean, this would contradict such an assumption. And then, of course, I mean, what's very interesting then is what would be the observational impact, what kind of observables could we have. And of course, I mean, one of the things that we also need to think about it, and there's still lots of work basically that one has to do, is to the evolution of magnetic fields. I mean, this is something which is not trivial, but we can basically use the observables in order to test basically our model. And of course, I mean, there are more questions that one has to address. But I mean, this is just to give you an idea, basically, what is involved in that. Okay, so the assumption that I'm working on is that these magnetic fields have the origin in the very early universe. So basically here we have the Big Bang, and then here first evolution, and we already, I think we heard already about the cosmic translation. So there are certain problems with the standard model of cosmology, and in order to solve them, one needs basically a period of expansion, very rapid, accelerated expansion, and one is to solve problems with the initial conditions, but also to provide the seeds, the initial small fluctuations, which later on give rise, once they enter into the nonlinear regime, which actually gives rise to all the large-scale structure, all the galaxies, etc., that we observe today. And okay, so here also we see then actually the cosmic background is formed. So up to that part, basically the universe is completely ionized. So we have the electrons and the protons, they're separate. So then also the photons, they're very strongly coupled. So they always scatter on the electrons. And so basically we don't see anything at some point. The universe becomes neutral, so we have a recombination, and then shortly after that we have the last scattering. So that's when the cosmic microwave background forms. So we have this image of this last scattering and all the fluctuations, and that's basically what we see in all these really nice pictures, for example, of Planck. And okay, so my assumption is, I mean, there are theories on one can actually show, one can actually elaborate and produce theories to create basically magnetic fields quite similar to these type of density fluctuations that we need. And we can also produce very small fluctuations in electromagnetic field, and they basically can give rise to this large-scale cosmological magnetic fields. And this is basically the assumption that I'm using. There are also other models which basically produce magnetic fields in so-called phase transitions, so like a battery mechanism. So one can also do. And as I already said, I mean, we need to think about how to actually model a magnetic field. And as I said, I mean, here we have these very, very small fluctuations in the temperature, and so this points towards a highly isotropic universe on very large scales, so we cannot really have a homogeneous magnetic field. It also has to be a fluctuating field, and so the simplest assumption is just to use a stochastic magnetic field and use the Gaussian fluctuations. And okay, so the most general part would be really a helical magnetic field, which also has an asymmetric part in this two-point correlation function. And this is, for example, what we see in the sun. There basically you have twisted field lines, and then you get these. But the important point in this is that the magnetic field is characterized by a two-point function, and this two-point function is basically has a power spectrum which is an amplitude and also spectral units. So that's here the important part. But basically, you introduce two new parameters, and this is just a cartoon on the different possibilities of the influence of the existence of a primordial magnetic field, because it has an influence basically on different parts of cosmological variables. So on the matter power spectrum, for example, on the 21 centimeter line signal, on the CMB temperature anisotropy polarization, also can generate CMB spectral distortions. And there are basically two different types of ways how a magnetic field actually can influence all these variables. And this has to do also with the evolution of the magnetic field. And this is something which is really non-trivial, because, I mean, magnetic fields, they interact with the cosmic plasma, and these are nonlinear interactions, and what it leads to is that that actually part of the magnetic field is damped. So part of the magnetic field actually decays, and this leads to additional heating of matter, because you have this energy has to go somewhere, and basically what it does, it's going into heating of matter. And there's the other part which actually does not decay, and so we have a positive contribution to the energy density, but also anisotropic stresses are created. And one of the important things is also that the baryon velocities are changed. And this is, as I showed before, the universe is ionized before recombination, and then the baryons basically they feel the Lorentz force, so this is also changed, and that's why they have quite a strong effect on the matter power spectrum. And okay, so these are all different aspects that one has to take into account, but it also provides the possibility today, basically, with all the data available, to actually test the theory and the understanding of the evolution of cosmological magnetic fields. So well, that point is also very interesting that now so much data is basically coming available. And this I just wanted to show you because of course, I mean, we are talking here about evidence. So of course what you would need in the ideal case is a signature, a unique signature of the physical theory basically that you want to test, right? So in this case, you would be interested in finding a unique signature of a primordial magnetic field. And a unique signature would be actually in the case of the helical magnetic fields. There's something very distinctive about it, because the helical magnetic field, it actually has the property that it generates odd parity CMB modes. So it would create basic cross correlations between the two polarization modes, so the E and the B mode, and also between the temperature and the B mode. And with once basically the polarization of the CMB is measured to a much more precision, then actually we can test also for that. I mean, and if one would find these type of cross correlations, then a good candidate could be basically a helical magnetic field. There are also other theories from particle physics, axioms, because I mean basically what you have to break, I mean you have to need some parity breaking theories, and one of them is basically axiom. I mean, so you can have non-standard physics breaking that, but it could also be a magnetic field, I mean helical magnetic field. So in these, since we know that magnetic fields do exist, I mean, this is quite, I mean this is not physics which goes, is very exotic. So it would be a very interesting signature of magnetic fields. And okay, just to show you now a particular example of all the different aspects of primordial magnetic fields, what I want to show now is basically to test one particular aspect of the theory of the evolution of magnetic fields, and basically this, what I said, that that magnetic fields actually dissipate part of the energy, and that this heats matter, and so this actually changes the thermal and the ionization history of the universe. So this is now a particular example that I want to show and compare basically with the data. And so this is just after coupling, because there are various ways of, it depends on when basically the magnetic field dissipates, if it's before or after decoupling, and after decoupling basically would be this part. And it's different. I mean, there are basically different sort of decay channels, so to speak. And okay, so this is just to explain the observations. Basically, the effect that it has is it changes this additional, as I said, I mean, it changes the thermal and the ionization history, and with that, actually, it changes what is called the optical depth close to decoupling. And so this is basically what this type of dissipation of the magnetic field does. I mean, it changes the optical depth, so the probability of scattering, I mean, because there are more free electrons. I mean, there's the whole basically the peak of visibility is a bit shifted to low redshift, and this actually makes the universe for a bit longer apart. So, that's due to the dissipation of the magnetic field. And this is what one actually sees here, for this type of magnetic field parameters. So we're talking 30 nanogauss, and these are the different spectral indices. And this is now really a particular example of using parameter estimation. And in this case, we just used, I mean, because I mean, also one of the things that is so fascinating and so now in cosmology, in those times that we are living, is that it's all basically most of the data are basically, after some period, they are basically open to the community, and and also there's open source software available. So basically, it's possible to really use those data and together with the software. And the software you can actually modify to the purposes, to the problem that you want to study. So it's much more, let's say, democratic today, because we have access to, I mean, we have access to all these data and all these possibilities, which was not like this, like 20 years ago or something like this. I mean, these days, if you have an idea, you can really go and test your idea. I mean, this is something which I find really fascinating. So, okay, coming back to the problem at hand. I mean, so this was done for the 2013 Planck data, and so everything is basically open, and for that we used basically class and Monty Python. I mean, these are two programs. I mean, so the class code basically calculates the spectra of the CMB anisotropies, and you can put basically, you can modify the code and include those effects of the magnetic field. And this part of the code in Monty Python actually does the exploration. I mean, does the Monte Carlos and explores the parameter space. And in this case, we have added, I mean, we have two more parameters. I mean, basically, it's the standard lambda CDM model. It has the 6 parameters, and then in addition, in this case, we also have the amplitude of the magnetic field, and to make it more handy, I mean, and not too expensive, basically, numerically. We just picked beforehand the spectral index, and then we just adjusted. I mean, we just left the magnetic field amplitude as a free parameter, in addition to the 6 other ones of the standard cosmological background, and then basically exploring the parameter space. And so this is for 3 different types of the spectral indices, and then one can find the best fits and best fit values. And here there are these typical 2D plots for basically the different combinations of the magnetic field with the cosmological parameters. And so the result of that was that one can actually use upper bounds on the magnetic field strength, and basically if we have a magnetic field which decays after decoupling, in that how it was modeled, I mean how we modeled basically this type of decay, then one could get that the field strength cannot be larger than 1 nanogauss. Actually, it has to be much smaller than 1 nanogauss. And this is for the different types of spectral indices. Okay, so this was really just one particular example that I wanted to present. I mean, it's really like a practitioner. I mean, it's not. For me, it's really. Okay, this is my, I mean, I'm interested in finding evidence of a primordial magnetic field, and basically what I'm doing is, let's see which kind of observables can I use for that, and in that case, I mean, was basically CMB, I mean, different types of CMB observables, and then test my theory against the data. And so just some points in general from that is then, okay, the cosmological magnetic fields. If I assume that I have a cosmological magnetic field which is really pervading the whole universe, then first of all it has to be small, because this we already know from the isotropy on very large scales. So this we already know from the CMB, for example. Then, one of the points that one observes with that is it's very difficult to disentangle from other effects. So far, there's no evidence where you would say, okay, this is a clear sign of that there has to be a magnetic field. I mean, the only thing that, for example, with the study I showed, I mean, there are upper limits on a magnetic field. It's not like in the case of the void magnetic fields where we actually have a lower limit. So there we actually need the existence of a magnetic field in order to explain those data. But in the case of this of cosmological magnetic, primordial magnetic fields, really, it's an upper limit. Okay, so what would be the prospects? What future directions could one take, for example, in order to go further with that? Is, of course, I mean, more data is always good. Also, different frequencies. So one of the exciting things also now is the shift now in the, basically also the cosmological, I mean, in cosmology is towards a 21 centimeter line study. So SKA, for example, is one big project which is going to observe there, and so this is also one of the effects where the magnetic fields also play a role. I mean, it's also what I'm studying. And also another point would be to cross-collate with different data sets. So, for example, with observations from galaxy surveys directly, because magnetic fields have a very strong impact on small scales of the matter power spectrum. And so this is also one of the things that one can look at. And of course, one also has to advance on the theory side. Because I mean, the theoretical understanding of the evolution of large-scale magnetic fields, and for that, basically, and there's also lots of activity, is numerical simulations. Because also magnetic fields, as I said, I mean, they are, I mean, galaxies, they have magnetic fields. So in the n-body simulations, there's basically MHD, I mean, so magnetohydrodynamics is implemented there, and there the codes are, the numerical codes are really advancing in that respect, and also to understand, I mean, the role of magnetic fields at the time of galaxy formation, for example. So it is very, very important. It's a very important point. And so, yeah, so I leave you with that. So, thank you.
So we have a little bit of time for a couple of questions, and we'll take a coffee break. Coffee? Any? Nora?
So I think this is just a question about motivation and about the history, just because I don't know anything about this. So, and maybe about the connection between the magnetic fields that might be in the voids and the idea of a primordial magnetic field. So, did the history go? You notice these absence in the Blazar data that you talked about first, and then people start to wonder about primordial magnetic fields. Is there no connection, or is there like higher theoretical motivation for the?
Yes.
Is there just sort of like good prima facie reason to expect that there ought to be primordial magnetic fields, and it's just a matter of finding them, or like, can you talk a little bit more about the motivation for looking for these things and the connection to evidence, and then if they relate to one another?
Yes, okay, thank you. So basically, these void magnetic fields is really something very, very recent. So this is from 2010. And yeah, so this is basically just one aspect. This came about, I think, because now there are more and more observations of these blazars. And so there were the observations in the lower energetic part, and this was missing. And then the explanation, which the model that people then, the groups basically elaborated, was, okay, this is an indication of a large scale void magnetic field. the part of the existence of primordial magnetic field, this is has a very long history. It's already from 1970. Basically, because I mean the thing is that the observation of galactic magnetic fields is also has a very long history. And then of course people started wondering, so where do these magnetic fields come from? Because I mean, you need a mechanism in order to generate these magnetic fields on galactic scales. And so that's why people came then up with the thing, okay, we have a galactic dynamo, and but for that we need an initial magnetic field at the point of galaxy formation. And then of course the next question was, where does this come from? So the idea of primordial magnetic fields has a long history.
I want to jump the queue to ask you, at some point you were describing a particular effect where the superposition of magnetic fields, one postulates them in order to explain the non-observation of an effect, and that's philosophically very interesting idea.
That's the thing of the blazars, exactly. It's a non-observation of that part.
So could you tell us a little bit more about how can we rule out any alternative explanations for the non-observations that would lead us to suppose that the magnetic fields are?
Yeah, that's also why this interpretation is still under debate. So it's really, there are the groups which work on those models that basically there's basically a void magnetic field which explains that. And then of course there are the other groups that say no, hold on, we don't really need that because there are certain caveats in that. So one of them is we don't really understand the sources. So these blazars, I mean, they are very okay. These are active galactic nuclei, but of course, I mean, there are also some part of that which is not really understood. So I mean, one needs more data on the blazars. So we have to understand those sources better. Then there are different assumptions, different assumptions going into those models. So for example, that these blazars actually have isotropic emission, that they don't change too much, so that there's not a lot of evolution. Then those data sets come from two different types of observations. So Fermi-LAT is one satellite which observes in the GeV range, and then these telescopes, HESS telescope. So there are different types of sets of observations. So we cannot really be sure that that actually those observations really are, let's say, we can actually directly take those data and put them in one plot. So to speak, I mean, probably maybe with calibration, etc. So there are basically groups which are which are against basically these interpretations. So it's still under debate. So there's an open debate, but there are several groups who basically say no. This is our interpretation.
And the alternative interpretations don't make use of the magnetic fields.
No, they just explain everything basically with sort of let's say ignorance. I mean, ignorance of the real model of the blazar, of the interpretation of the data. So they say that the uncertainty is that basically the non-observation can be inside the uncertainty of the interpretation of the data.
Right. So there's no need to explain.
Exactly. That's what. Yes.
That's very helpful. Very interesting. Thanks.
Oh yeah. Thanks. Thank you very much. Forgive me if this is not really a question. It's just an association or something I had to think about. So just wanted to throw it out there because at one point you came to the conclusion that you said we need this magnetic field to explain the data. And in another moment you said it's an indication of the existence of a truly cosmological magnetic field. And so then I had to think about, because in different ways you also call it evidence, right? It's evidence for the existence of this field. So in a certain sense that I was thinking about in what sense evidence is in that sense also the explanation of the phenomenon. So here the magnetic field you imply that should exist. Then yeah, I was just trying to struggle with the relation between the explanation or the need to explain something is the evidence, right? That the need for a magnetic field to explain the data is the evidence for the existence of the magnetic field, which I found an interesting correlation between both. But yeah, I'm not sure if and then I had to think, of course, of the question that I got on in what sense can you talk that evidence makes that certain scientific objects come to exist. Well, here it's quite clear, but of course the idea of existence is still something which should be a bit more sensitive. But here we talk of the existence of a magnetic field because of certain evidence, because of the way that you kind of put all these data together, you added them up in a beautiful visual, and you said, hey, look at this. This is actually, this together makes that there's evidence for the existence of this magnetic field. So, yeah, it wasn't really, perhaps it's something for the discussion later, the relation between explanation and evidence, but I just wanted to throw it out there. I'm not sure if you have a comment.
Yes, certainly. I mean, it's like, when I was preparing this, I was also thinking about this. I mean, it's like I'm trying to be more precise with the language, but it's very it's difficult. No?
Yeah, when you start concentrating on that, you're conscious of it.
Yes.
You kind of then you see that you have different ways of formulating the same idea, right?
Exactly.
The fact that it should exist, the fact that it explains, the fact that there's evidence,
Exactly. So one really, I mean, I actually feel then the need to actually to define what is evidence. Is it more than, I mean, is it only direct? Because I mean, of course, I mean, as I said, I mean, magnetic fields in the universe, this is not direct observation. One always needs something, radiation or something like this, in order to pin it down. And so then I have my theory, which I test basically, and from that I deduce the presence of magnetic fields. But is this then evidence for magnetic field, or would I only say evidence can be something which is directly observed? So.
Well, your model is not complete, and you need magnetic fields to complete it.
Yes.
And the theory can be wrong, and all of these things.
Yes.
So you have a lot of solutions for the problem. So it's an evidence that something is intact, something.
Yes.
On your model, on the theory, it's in place.
But then, of course, I also apply, let's say, open Fraser, because I want to have, or maybe also what was mentioned this morning, naturalness. I mean, the natural, I mean, because of course, maybe one could also invent some sort of, very exotic theory, and with some exotic matter or particles or whatever, and explain also this type of data. But then I'm saying, okay, I want something like a magnetic field, which I know exists in other scales. I already have direct observation of magnetic fields, and if I can use a magnetic field to explain that, it seems sort of natural.
Yeah, I think, for instance, that if you have a net explanation of different things, and 3 or 4 things point to the whole magnetic fields of the universe, then you have an evidence.
Yes.
Now you have something like,
But why? Why?
Because if they are not related in you have 4, 5, 6 theories, models, in different subjects. For instance, and all of them point a magnetic field, at least a cosmic magnetic field, then you have, I think you have strong evidence that you need this, not just for this, for solving this problem, but for solving problems that are not relating in these theories.
Yes.
You know what I mean? If you are adjusting parameters, and then I need this, and I can say that, well, I need to transform this into this.
Yes.
Like you have different theories in different subjects, and you need the cosmic magnetic field. That's why I have a really strong evidence that we need a magnetic field, and the magnetic field is this. So if someone is needing these magnetic fields for all the theories or all the models, it could be really good for you.
Yes. Well, that's what I'm saying, like Brownian magnetic fields, galactic magnetic fields, etc. No? I mean, this is
I've made notes for the final discussion.